And the slides which I have prepared up till now are from the textbook. Okay, but I have to recheck it if I can continue with the same book, because I feel it has less problems. Okay, so I will check the remaining, and maybe I may change the book. Okay, but up till now it is from the textbook. Okay, what is statistics? Statistics is the science which is concerned with gathering, analyzing, and interpreting the data in order to get maximum amount of useful information from that. Okay, so if somebody gives you the data, what are the methods in which you will analyze the data so that you can get most useful and most useful information from the data set? That is what we call as statistics. Okay, and we have discussed statistics in the last topic as well. So the data which you normally collect for anything, okay, like I mentioned earlier, that even if you are doing data collection for lab testing, that also follows the same rules and regulations. Okay, so that is also a sample. Okay, so data usually consists of a sample which is taken from a population. Okay, so a sample would be the samples which you have prepared and tested, and the entire population will be whatever is available to you. Okay, but in no way it is possible to collect the data for the entire population. Okay, whether you are doing it for transportation or business or lab testing or whatever, it is not possible to collect the data for the entire population. You always rely on sample of values. Okay, because collecting the data for the entire population is not economically feasible. Okay, it will require a lot of efforts, it will require a lot of time, it will require a lot of people, and even if you collect the data, then you need a lot of effort to analyze it. Okay, so dealing with 100 values is more convenient as compared to dealing with 100,000 values, right? And in some cases it may not be technically feasible as well. You may not be concerned with the entire population. For example, if I'm talking about the drivers, I know some drivers are very bad, some drivers are very good. Okay, but I'm not going to base my design on these exceptional drivers, very good and very bad. Both cases are exceptional. I want a normal range. So even if you give me the data of the entire driver population, I will not use the extreme values. Okay, so even on technical grounds, it is not feasible to collect or try to collect the data of the entire population. Okay, so now since you are relying on a sample and you are trying to collect the data of the sample, then there are two questions you need to answer. When you're collecting a sample, there are two questions you need to answer. How to ensure that your sample is a representative of the population? Okay, now for example, in your term projects, now I have given you a questionnaire and I've told you that you have to collect these many values from each category. Okay, I have given you the values, right? I have told you that from each category you take these many samples. That may not be the true representation of the population of Bahrain. Okay, one of you may come up with, for example, let's say 40% data for, let's say, Bahrainis and 60% data of non-Bahrainis. The actual population of Bahrain may be 50-50%. So the data which you are gathering is not a true representation of the data of the population of Bahrain. Okay, or someone collects, let's say, 30% values from female and 70% values from male. Again, it may not be the true representation of the population of people living in Bahrain. Okay, so for academic purpose, okay, this is fine because we are doing comparison and so on and so forth. This is fine, but actually your sample should be a representative of the actual population. The actual population has 50-50% Bahraini, non-Bahraini, your data should also have the same proportion. If the actual population has, let's say, 60% female, 40% male, then your sample should also have the same proportion. Okay, so how to ensure that your data or your sample is a representative of the actual population proportions? Okay, and then the second question is, if the sample satisfies the above condition, it is a representative of the population. How to extract useful information from that sample? What type of analysis should I perform? How should I use the data to get the required information from the sample? This is another important question. Okay, before we move on to the calculations, let us discuss some of the terms which we are going to use again and again. Okay, so sample means a collection of units which is specially selected to represent a larger population of interest. Okay, so our sample is a collection of units. Okay, units of what? These units are especially selected to represent the population. Okay, that's what I said in the previous slide as well, that you are selecting some of the units from the population, that these units are representative of the entire population. Okay, and each of these units has certain attributes which you are observing for them. For example, their height, their age, their income. So for each sample, you are collecting some attributes. Okay, the height of the person, the age of the person, the income of the person. So that is the collection of these attributes for some of the units of population is what we call as a sample. You can see some of the terms are underlined here. So these are important terms. So the first term is collection of units. So it's not the entire population, it's some of the units of the population. Second term is especially selected. Okay, and this will bring us to how should we select the sample? How should we select the sample? Which units, from which parts of the population should I collect the data? I cannot collect from all, then from whom should I collect the data? Okay, and the third thing is the important point, that whoever is selected should be a representative of the normal population. Okay, then we have population of the interest, the complete group about which you want the information. So you actually are trying to find out the information about the population of interest, but since you cannot cover the entire population, you are taking a sample from it. Okay, so the group from which the sample is taken. Okay, the group from which the sample is taken. Okay, and how should I define that group? This depends upon the objectives of your study. The objectives of your study. So if your study is only limited to a city, then your population of interest will be the population of the city. If your objective of the study is to cover entire Gulf region, then your population of interest will be the entire Gulf region, and so on and so forth. Sampling method. Okay, sampling is this thing. Okay, it is focused on this thing. Selection of units in the sample, basically. Sampling method means how should I select the samples for which I will collect the data. Okay, that is the sampling method. In most of the cases, random sampling or some variation of random sampling is allowed. Random sampling means what? Random means no selection of the data. Okay, so obviously earlier I was saying especially selected, but in many cases we don't want to select. We don't want to do the selection ourselves. Random sampling means I'm not doing the selection. Okay, I'm not saying that I will collect the data from Muhammad or from Sayyid, from Ali, from Safa. I will not say that. Okay, I will do it randomly, and if the data comes from Muhammad, fine. If the data comes from Unab, fine. Okay, and so on and so forth. So random sampling. Random means that now you are not selecting anyone. Whoever is willing to respond, or whoever is willing to give you the data, or whoever is coming at the time of your data collection, you will collect the data for that. You will not say, I don't like this person, or this person is very rude, let him go, I will ask someone else. This is not random. This is not random. Okay, random means whoever comes in your data collection time, you will collect the data from him. Okay, so simple random sampling, that is the simplest method, but it is also the basis of other methods of sampling as well. Other methods of sample collection also have some part of randomness in them. Okay, So the easiest way for random sampling is, for example, you have 100 households in your area. Okay, you have 100 households in your area. So to each household, you will assign a number. Okay, 1, 2, 3, 4, 5, whatever number. Okay, or 100, 200, 300, whatever. So to each household, you will assign a number identifier. Okay, and a label to each household. So the household at this location has a label 1. The household at this location has a label 3, and so on. Okay, whatever coding you can use, whatever coding you like. Okay, you can code according to the street, you can code according to the location, according to income, whatever. Okay, so you code the household, and then you put this coding in a table or in a column. Okay, then you can put it into MATLAB, you can put it into Excel, and you can generate random numbers. Okay, you can ask Excel to generate, or MATLAB to generate random numbers for you. And to which of the household this random number matches, you will collect the data from that household. Okay, so for example, there's a command in Excel for random number generation. Okay, there's a command in Excel for random number generation. So you use this command. For example, you are going to collect data from 15 houses. Which 15 houses? I don't know. Okay, so I assign the house number from 1 to 100 in the area. Okay, now I'll go to Excel. I'll use the command of random number between 1 to 100 15 times. So each time Excel will give me one number out of 100. Okay, now that number belongs to whichever household, I will collect the data from that. Okay, this is the basis of random sampling. Okay, that it is done by assigning some identifier to the population units, and then you select the identifier randomly. Okay, you want to spin the wheel, or you want to generate random numbers from Excel or MATLAB, or you use any other method. Okay, or you know do some polling or something. Okay, write the numbers on a piece of paper, and then you throw it, and then you pick the pieces of paper randomly. Any method you like. Okay, random sampling. Okay, so you assign the identifiers, then you pick the identifiers randomly without any biasness from your side, without any intentional effort from your side to pick a specific number. Okay, that is simple random sampling. Then we have stratified random sampling. Stratified random sampling is something similar to segmented modeling, the last thing which we did in the previous chapter. So you know about your population, that in your population I can divide it into on the basis, I can divide it on the basis of gender or income or whatever, location, whatever. Okay, so you divide your information into segments which are similar to each other. For example, you divide your population on the basis of income. Okay, so high income household, lower income household, middle income households. Okay, and then you take a random sampling from each segment of the households, each segment of the population. So in the first method, you did not divide the population into any segments. In the second method, a stratified random sampling, you are still collecting samples randomly, but not across all the segments. Okay, you have already selected that I will take these many samples from this segment, these many samples from this segment, these many samples from this segment. Okay, then within the segment you pick them randomly. So if you had 100 households, out of 100, 20 are lower income groups. From 20, you will pick 5 randomly, for example. Okay, then the middle income group are, let's say, 40. So from these 40, you may pick 10 randomly. Okay, but all those 10 will be from that specific group of population. So this is a stratified random sampling. Okay, and in each stratum means segment. Stratum means segment or part of the population. So each stratum or each segment of the population is homogeneous in their characteristics. Okay, they are similar to each other. Okay, and then you pick a sample randomly from each stratum. Okay, then we have choice-based sampling. Now, choice-based is more advanced because now you are collecting samples randomly according to the choice of the travelers. So according to basically the output which you want from the sample. Okay, so for example, you may collect samples from people who are choosing to go by bus and by car and by taxi. So you have three groups, and these groups are not made according to the characteristics of the people. They are made according to the choice of the people. Okay, this is the main difference between the second and the third option, the stratified random sampling and choice-based random sampling. In a stratified random sampling, I picked a characteristic of the population, and then I divided the population according to its own characteristic, like income or location or height or whatever, or gender. But in choice-based sampling, I'm dividing the population according to the choices of the people. Okay, so like people choosing to go by highway 1 or highway 2. This is a choice. Okay, so in a stratified sampling, I was dividing the samples according to the population characteristic. In choice-based sampling, I'm dividing the population according to the choice of the travelers. Okay, so choice is basically the output. Okay, but the characteristic of the population is an input. Okay, you cannot change your income, you cannot change your height, you cannot change your location, but choice you can change. Okay, so that is the output. Okay, continuing with the other definitions, then we have sampling error. So since we are collecting data from a sample and sample cannot be exactly equal to the entire population, so there will always be some random errors present in the data. Okay, this is true and this cannot be avoided. Having some random errors cannot be avoided because the data obviously is for a population, not for the entire, for a sample, not for the entire population. Okay, so sampling error is a function of sample size and the variability of the parameter under investigation. Okay, sample size, basically if you need less sampling error, then you increase the population size. Simple. You collect more data, sorry, not population size, sample size, sample size. If you collect more or a bigger sample, sampling error will be less because now your sample is closer to the population. What was the major difference between the population and the sample? The size. So if you increase the sampling size, increase the sample size, then you are becoming more and more like the population. Sampling error will be less. Okay. And secondly, the second point is variability of the parameter. So you are looking to collect, basically your purpose of collecting the data is to find out the number of trips. So if there is more variation in number of trips of different people of the population, then sampling error will be higher. Okay, so if everybody is taking, let's say, 1 or 2 trips per day, okay, there are very few people who take more than 2 trips per day. So since the variability is less, so sampling error will be less. Okay, and vice versa. So there are many people who are taking 1 trip, many who are taking 2 trips and 3 trips. So it is evenly distributed. The number of trips are evenly distributed among different people, and so it will have a lot of variation. In that case, the sampling error will be more. Okay, let me give you an easier example. Maybe it will clarify more. Now, for example, if I say I only need the data about the grades of postgraduate students. Okay, maybe in the entire department I will have 20 postgraduate students. Okay, there's less variability in them. Smaller population, less variability. Okay, if I tell you I need the data about people who are doing a specialization in structures. Okay, now I'm from transportation, but obviously a structural group is bigger, so it makes sense to collect data from them. Okay, otherwise transportation group 2 people, no problem. Okay, so let's say if I tell you from the postgraduate students, I only want to collect a sample of grades from the people who are doing specialization in structures. So now the variability is further reduced. Okay, so sampling error will be less. Okay, now if I tell you I want the grades or a sample of grades for all students in the department, all students in the department. So this is now a lot of variation, right? This has a lot of variation. Undergraduate students, graduate students, then within undergraduate students I have different levels. Okay, so now I'm increasing the variation, so sampling error will be higher. Okay, so whatever parameter you are collecting, if that parameter has more variation, the sampling error will be higher, and vice versa, but you can reduce the sampling error by increasing the sample size. Okay, you can eliminate the sampling error. You can yeah, you can eliminate the sampling error by collecting data in different stages. So you collect few samples, then you see how much is the variation, then you collect on the basis of that variation, you decide how many more samples should I collect, and so on and so forth. So you can do them in stages, but obviously it requires a lot of effort. Collecting data one time, easy, convenient. Collecting data multiple times, more problematic. Okay, then we have sampling bias. Okay, sampling bias is caused by, so biasness means inclination towards a particular site, right? This is biasness. So sampling bias is caused by mistakes which are made either when you are defining the population of interest, or when you are selecting the sampling method, or the data collection technique, or any other part of the process. Okay, so you did not define your population properly. Okay, you were trying to collect, you were trying to plan for the entire city, but you focused on the central part of the city. Okay, you said whoever was collecting the data, you told him just collect the data from this area of the city. You did not define the population properly. Okay, or the trips which are coming to your city are also coming from outside the city, and you forgot to include them in your population. Data will be biased. Okay, so sampling error means, now okay, there's a difference between sampling bias and sampling error. Sampling error means the difference between the actual value and the value of the sample. Sampling biasness means that your sample is not representing the population. It's not representing the population properly. Okay, so that is sampling biasness. So either you did not define the population properly, you missed something in defining the population, like I just mentioned, or you did not take the sample correctly. So your sampling method was not correct. Like I said, maybe you were selecting the samples on the basis of your interest, on the basis of your convenience. Okay, that I can go to this area conveniently, it is near my house, let me collect the sample from there. Or people who belong to this category, they respond very easily, let me collect the sample from there. This will be biasness. Okay, or maybe the data collection technique was not good. You require data from lower income group, but you are relying on online questionnaires. Or you require data from different education categories, but you are relying on online questionnaires. Then obviously the data will be biased. Okay, or you made a mistake in any part of the process. Okay, sampling biasness will affect the variability of the parameter, because obviously if I ask you collect the data for all the students and you only give me the students of postgraduate, then obviously you are playing with the variability. If you gave me the actual data which was for all the population, for all the students in the department, the variability would be more. So sampling biasness will affect the variability of the parameters. Okay, it will affect the values as well as the variability in the values. Okay, the variation in the values, and it is considered to be a bigger problem than sampling error. Sampling error, like I said, you cannot avoid it, but sampling biasness should not be there. Sampling biasness means that you made a mistake. Okay, so you can see they are using different words here. Error cannot be avoided, mistake should be avoided. Okay, so they are using the word mistake here. Okay, sample size, how many samples should be collected? For your term project, I made it simple. I gave you the value. Okay, these many samples from each category, and that's it. Okay, but sample size should be calculated using some equations, some formulas. Okay, and they should have some statistical background behind them. Okay, but the problem is that the things which you require to calculate sample size, some of those things may be unknown before you collect the data, or some of the things may be subjective. Okay, give me a second. For example, if you ask me the mean population, the mean income of the population, without collecting the data, I cannot know the mean income population, right? Secondly, you may ask me how much error do you want, how much error you are accepting in the population. I may say 5%. Mohammed may say 4%. Safa may say 10%. Okay, so this is subjective. Okay, so but these are the inputs which are required for calculating sample size. So you have to play with it. Okay, so it's not easy. It's not easy. Okay, this is what I'm trying to say here. So you have to negotiate between two parameters. Okay, either you end up collecting too large sample. Okay, try to collect as many values as possible, but that will be expensive. Okay, and it may be unnecessary if the study does not require so much accuracy, or the objectives of the study are not so broad, are not so important. So you are collecting sample just to show that my signal works. Okay, or you are collecting sample just to show that this highway is used more than the other highway. Okay, so you don't require so much accuracy in these things. Okay, so the too large sample may be expensive and unnecessary depending upon the study. Or you may end up collecting too small sample, a sample which is very small, and this can mean that you are you are increasing the variability of the data. If you collect a sample which is very small, you may end up having values which are completely different from each other. So you have 5 values and they are not close to each other at all. So one value is 1, the other one is 100, the other one is 300. What to do now? What conclusion can I make from a sample like this? Okay, so you have to do something between these two extremes. Don't make it too large, so it will be unnecessarily expensive. Don't make it too small, so that the variation is too high. Okay, something between them. Okay, how to calculate the sample size? Sample size depends upon 3 things: the variability in the parameter, the degree of accuracy you require, and the size of the population. Okay, now there is a theorem which we use when we are calculating the sample size, and this theorem comes from normal distribution. Now, normal distribution is something which we discussed last week with the random variable distributions which we were discussing. Okay, so normal distribution, bell shape, z value, and so on and so forth. So why are we applying a theorem for normal distribution to sample size? Because according to researchers, any sample which is taken correctly from a population, it should follow normal distribution. Any sample which is taken correctly for a population should follow normal distribution. So that's why we can apply the central limit theorem, because central limit theorem is for normal distribution of data, normal distribution of variables. Okay, what does central limit theorem say? Central limit theorem says that if you want the mean of samples, okay, so according to central limit theorem, the mean from a sample tend to become normally distributed as the sample size increases. Okay, as the sample size increases, the mean of the data set, yeah, okay, as the sample size increases, the mean of the data set becomes close to normal distribution. Okay, so normal distribution means it's a bell-shaped curve. Let me draw it. What is the normal distribution? A normal distribution looks like this. A bell-shaped curve, mean in the middle, half of the values on one side, half of the values on the other side. Okay, so central limit theorem says that if you collect enough samples, then the mean will follow normal distribution. The mean will be in the middle somewhere. Okay, the mean will be in the middle somewhere. Okay, and what does they mean, or what do they consider as enough values? According to central limit theorem, number of values you are collecting, if they are at least 30, then you can apply central limit theorem to that. Okay, so if you want to believe that the mean of your population follows normal distribution according to central limit theorem, then you should at least collect 30 samples. At least. This is a minimum value. Obviously, I will show you the equation to calculate the actual number of values. Okay, so yeah, so the here you see the standard error for x bar. Now what is x bar? X bar is the mean of the sample. X bar is the mean of the sample. Now the standard deviation or the error in the mean, the standard error in the mean. This is the standard error in the mean. Okay, so the sample which you are collecting, how much should its standard error be? Okay, this can be calculated using this equation. So you can fix the value of the error and you can calculate small n. Okay, now what is capital N? Number of samples in the entire population, number of values in the entire population, that is capital N. What is small n? Number of values in the sample, the one which you want to calculate. So we are trying to calculate n here, small n. Okay. What is sigma square? Sigma square is the variance in the data. Variance in the data, variability in the data, this one. Okay, so like we said, we need three things to calculate the sample size: variability in the data set, which is sigma square; degree of accuracy, which is given by this one, standard error of the mean; and population size, which is given by capital N. Okay, and if you have only one sample, this is if you are taking many samples, then you can calculate sigma square using many samples. But normally, obviously, we are calculating one sample, and in the case of one sample, then the equation will be simplified to this one. Okay, if you are just calculating or just finding the values for one sample, then this is the simplified form of the equation. Okay, but again, you can see the parameters are the same: n number of values in the entire population, and small n number of values in the sample which you want. S square is now the variance of the sample, and so on. Okay, so another equation to calculate a standard error for the mean is s upon root of n. Okay, why did we make the equation into this one, or how did we make the equation into this one? Because this ratio n minus n upon n tends to be 1 normally, or close to 1. Okay, for most of the cases, n minus n upon n is very close to 1. N minus n upon n is very close to 1. So you take n minus n upon n from here and you put it equal to 1. Okay, so we took n minus n upon n and we put it equal to 1. Now why is that? Why is that? Can someone tell me why I am saying that n minus n upon n is almost equal to 1? Capital N means number of values in the entire population. A small n means number of values in the sample. Now, can someone tell me the reason that this is almost equal to 1?
Doctor, because the sample is almost too much less than the actual number.
Yes, yes, yes. So normally the sample is maybe 1% or even less than 1% of the entire population. So in that case, n minus n upon capital N again will be almost like you are dividing n with n itself. Okay, so that's why it is most of the times equals to, or it is almost equal to 1. Okay. So if you put this entire ratio equal to 1, then the final equation becomes very simplified, which is this one. So this was the initial equation which can be applied to number of samples, then the simplified form for one sample, and then in that simplified form we replace the ratio n minus n upon n equals to 1, and then we got this simplified equation. Okay, now in this equation obviously I'm not trying to find out a standard error, I'm trying to find out what? N. Okay, I'm trying to find out n. So you modify the equation. Okay, rearrange the values. So n on this side and the other parameters on the other side. Okay, so we have s square here, which is the variance in the sample, and we have a standard error of the mean. Okay, on this side. Okay, so now this is the way you can calculate the number of samples required. Okay, now if your population is finite, finite meaning you know the number of values in the entire population. Sometimes we don't know the exact value. For example, if you say population of Gulf countries, or for example, if you say number of drivers on the road, so I don't know how many drivers are on the road. Okay, so in that case, I will just simply use this and take the number of samples from here. But if in a particular case you know the value of the entire population, how many drivers in their Bahrain are there in Bahrain, I know that number, then I can apply the correction to n dash. Okay, and this is the correction for a finite population. So somehow you can see in this equation capital N is not required. Okay, so somehow you can know the value of capital N, then you can apply the correction factor. Okay, and you will end up collecting less values. Okay, you will end up collecting less values. So if you don't know the size of the entire population, then because there is more uncertainty, so then we will collect n dash. Okay, which will be higher. If you know the size of the entire population, you can apply the correction factor, and then you will collect only n values, which is less than n dash. Okay. Okay, so whenever you are collecting sample size, first thing you need to determine is what is your confidence level. Okay, what is your confidence level which you want from the observations? How confident you want to be about the observations? Okay, or what range you are willing to accept for the entire population. For example, if you say I want to cover 95% of the entire population range, then your confidence level is 95%, and that means what? Your error is 5%. I want to cover 95%, so I'm foregoing how much? 5%. Okay, so first of all you have to determine what is your confidence level. Okay, from the mean. Now mean is in the middle. Mean is in the middle, like I showed you here. I'm assuming a normal distribution, so mean is in the middle. From the mean, how far I'm willing to go for the entire population. Okay, so if I want to go, for example, from the middle, I want to go 95% on either side. Okay, so I'm trying to cover 95% population. Okay, so this is what you need to determine. This is what we call as a confidence level. Okay, and the interval which you will get 95% for 95% of the entire population will be known as confidence interval. How much confidence interval you need around the mean, meaning how much population you want to cover. Okay, so if you are assuming normal distribution and you are going for 95% confidence level, again you can see, although the previous chapter we were doing it from a different book, this is from a different book, but again you see they are still using 95% confidence level. Okay, so you want to cover 95% of the entire population. Okay, now according to central limit theorem, 95% confidence level is this range. Okay, the number which you see in the bracket is confidence interval for 95% population. Okay, which is what is mu? Mean. Mu means mean. And what is sigma? Is standard deviation. So if you do mean plus minus 1.96 sigma, that will give you 95% confidence interval for the entire population. The range for 95% of entire population. This is again a postulation of central limit theorem. Okay, so from the mean, how much I'm willing to go forward and backward? 1.96 sigma. From the mean, I'm willing to go 1.96 forward and 1.96 sigma forward and 1.96 sigma backward. Okay, so to cover 95%, I have to go 1.96 sigma forward, 1.96 sigma backward. So this becomes my standard error. This 1.96 sigma, which I'm willing to go forward and backward, this is the error I'm accepting in the mean. This is the error which I'm expecting, or I'm accepting in the mean. Okay, and then so from the confidence interval, I know that whatever error I will fix, it will be equal to 1.96 sigma. Whatever error I will fix, this will be equal to 1.96 sigma. Okay, and the client says that I'm willing to accept 10% error. Okay, so for 95% confidence interval, I should do 1.96 sigma forward and backward, and this 1.96 sigma, according to the client, should not be more than 10% of the 10% of the value. Okay, the error which you are allowing forward and backward to cover 95% population should not be more than 10% of the values. 10% of the values. Okay, so this is according to central limit theorem, and this is according to the client. Client is saying from the real mean, I can go plus minus 0.1 forward and backward. So this means what? 0.1 mu equals to 1.96 sigma, because this is standard error allowed by the central limit theorem, and this is the error which is allowed by the client. So they should be equal, right? If I want to collect enough samples which is fulfilling the central limit theorem, which means I'm getting 95% of the data, and at the same time the error does not go above 10%, that means 1.96 sigma should be equal to 0.1 mu. Okay, so this is what they are saying here. Their standard error equals to 1.96, oh sorry, 0.1 mu, or so it was basically this is sigma. Okay, this is sigma. Okay, let me write the equation here. So what I'm saying here, 1.96 sigma equals 0.1 mu. Okay, 1.96 sigma is what? The error which you need to incorporate to cover 95% confidence level. And what is 0.1 mu? The error which is allowed by the client. Okay, so they should be equal. So sigma is a standard error. Okay, SE, we represent it with SE. So SE or sigma standard deviation is the same thing. Okay, so sigma will be replaced by this. So SE equals 0.1 mu upon 1.96. Okay, and if you do that, then 0.1 upon 1.96 will give you 0.051 mu. Okay, and if you put the value of a standard error of x bar in the equation of n dash, so if I replace this value with this value, okay, then I will be having this. So s upon 0.051 mu and complete square. See here, it was s square, and this was also a square. Okay, this was also a square. So square was taken for the entire bracket then. Okay, so s is standard deviation, and we replace standard error of x bar with 0.05 mu from here. Okay, so I took the error which is allowed by the confidence interval and I made it equal to the error which is allowed by the client. Okay, and I calculated the value of standard error of x bar, then I put it in the equation of n dash. Okay. Now 0.051, if you do 1 upon 0.051 square, so whatever number you have here, what? Let me write it here. So n dash equals s square upon mu square. Okay. 1 upon 0.051 square. Okay, you can write this thing in this manner, right? Okay, so if 1 upon 0.051 and then you do the square, you will get 384. Okay, so what is 384? This bracket. 384 is this bracket. Okay, now you see here CV. CV. Now CV stands for what? CV stands for coefficient of determination. CV stands for coefficient of determination. Okay, which is basically it is standard deviation upon mean. Okay, the standard deviation upon mean or coefficient of variation, it means the same thing. Okay, and then obviously then you have the bracket which is square, so that's why you see CV square. Okay, so standard deviation upon mean is what we call as coefficient of variation, and you can represent it with CV. Okay, so in this case, in this particular case, number of samples will be equal to 384 into CV square, where CV means standard deviation upon mean. Okay, so if you want to calculate the number of samples, then you should know the mean and the standard deviation of the sample, and you can calculate the number of samples from this equation. Okay, so we started from where? We started from confidence level. First of all, you have to determine the confidence level. Then you go to central limit theorem and you see for this confidence level how much standard error is possible. Then you put it equal to the error which is allowed by the client, 10% of the mean. Okay, so when you put it equal to that, you will get the value of a standard error. Okay, and then you can put it back in the equation of n dash. Okay, and like I said, if the number of samples in the entire population is known, then you can apply the correction factor as well, this correction factor. Okay, let us assume that we have m observations which are required for each cell. Okay, so you can see there's a table which is given, and the table there are different categories which are mentioned here, different categories of data which are mentioned here. So we have people who have with car and without car, and then with car we have two types of households, smaller households which have 4 or less members, and bigger households which have more than 4 members. So households, the smaller households with car are only 9%. Big households with car are 16%. The small households without car 25%. Big households without car 50%. Okay. Now let's say from each of these categories I need m values. From each of these categories I'm trying to find out m values. Okay, so what should be m? Okay, what should be m, and how much confidence level I'm trying to achieve? 95%. 95%. Okay, so we have two options available to us. Okay, first option is that you collect values randomly. First option is collect values randomly. So go to each household randomly. It may have car, it may not have car, it may be a big household, a small household. No problem. I will just go there and I will collect the data randomly. Okay. So how many samples should I collect randomly to make sure then from each category I have m values. In each category I should have m values. Okay. Now if all categories, if all the categories in the last column had equal proportion, so all of them were, if all of them were 25%, 25%, 25%, 25%, no problem. Collect m value. Sorry, you collect then 4 times m. 4 times m, right? One for each category, no problem. Okay. But since when I go to a household randomly, I have more chances that this household will belong to this category than it belonging to the first category, right? Because in the entire population, there are 50% household which are without car and big households. So if I go to any household randomly, that household being a big household without car has more chances of it being a small household with a car. Okay, so any household chosen randomly has more chances of belonging to this category than to this category. Okay, so since this is the case, so I cannot collect 4 times m values randomly, because if you do that, then obviously in this category you will have more values, and this category you will have less values, in this category you will have even less values, and so on. So all of them will not be equal to m. In this category you may have more than m values, and this category you may have less than m values. Okay, so how do I make sure that I can go to the households randomly? I choose any household randomly and still ensure m values in each of the household. Okay, so what we will do, we are saying that, so we will take the category which has the least proportion, the category which has the least proportion, which is this one. Okay, so if you collect n values, n is the number of samples, right? N is the number of samples. So if I go to households randomly and I collect n values, n number of values, okay, out of those n values, if my randomization was proper, if I did the randomization properly, then out of those n values, 9% would belong to this category, right? This one, and 16% will belong to this category, and 25% will be for this category, and 50% will be to this category. So if 9% of n is equal to m, then obviously for the remaining categories I have more than m values. You get my point? If 9% of n is equal to m, then obviously the remaining categories will have more than m values. Why? Because you went to households randomly. 9% of the households which were chosen randomly were belonging to the first category. So if those households are equal to m, then the remaining will be more than m. Okay, so if now try to understand the assumption behind it. The assumption is that these percentages are true, they are accurate. So the actual population does have 9% from the first category, 16% from second category, and so on. And second assumption is that you did collect the samples randomly. So if you collected the samples randomly, then 9% of those samples will belong to the first category. Okay, so 9% of n, okay, now I'm talking about this n, 9% of n should belong to the first category. Okay, so if 9% of m, 9% of n, okay, n for what? N for nuclear, right? So, or n for new. So if 9% of n equals to m, m for monkey, right? So if 9% of n equals to m, then the remaining cells will have more than m value, because remaining cells are, for example, for this cell you will have 0.16 of n, right? For this cell you will have 0.25 of n. For this cell you will have 50% of n. So whatever samples you are collecting, for example, if you collect 100 samples, okay, so if those samples are collected randomly, then 9 of those samples will be from here, 16 from here, 25 from here, and 50 from here. Okay, so if m equals to the lowest category, then in the remaining categories you are having more samples. So if m equals to 9, then the remaining categories have more than 9. If m equals to 20, then the remaining categories will have more than 20. So if I can ensure enough samples in the first category, the remaining 3 categories will automatically have more than that. Okay. So to ensure that I have m samples, m for monkey, in the last category, in the least category, I will put m equals to 9% of n, because this category has 9% of the entire population. So if m is equal to 9% of n, remaining categories will have more than m. Okay, so m equals to 0.09 n, and if you put n on one side, everything else on the other side, so the number of samples you should collect is 11.1 m. So if you want to have, let's say 10 values at least in each category, then you should collect 10 into 11.1, which will be 111. You should collect 111 samples, so that would make sure that you have 10 at least in each category. If you are saying that I need 15 in each category, then n would be 15, and 11.1 into 15 will give you the number of samples. Okay, this is the first option where you are collecting the data randomly, completely randomly. Okay, second option is you go around the entire population, or sorry, you collect a random survey of 11.1 m households, whatever m you are requiring. Okay, so like I said, if you're requiring 10, then you will collect data from 111 households, 111. Okay, 10 into 11.1, 111 households. You will collect random samples from 111 households, and you will just ask them to which category they belong, to which category they are belonging. Okay, from those households, just ask to which category they are belonging. Okay, so I go around 111 households. If m is 10, then you go around to 111 households and you ask them to which category of data they belong. So some of them say we have 4 or less members and we are with car. Some of them would say we are more than 4 and we are with car, and so on and so forth. So from these 111 values, from these 111 households, you know how many belong to 9% category, how many 16%, 25%, 50%. Okay. Then now remember, you have just asked them 2 questions: how many members in the household, and do you have a car or not? So this is not the complete survey. Okay, so now you will do another round of survey. So the first round was to find out of the 111 which category they belong. Okay, in the second part of the survey, in the second round of the survey, you will select. So I know out of 111, let's say 20 belong to the 9% category. Okay, but I only need 10 samples, right? I only need 10 samples. So from those 20, which I already know now, so for those 111 households, I know exactly their category. Okay, so I don't have to do the entire survey of the 111 households. I only need 10 in each category. So I will do the final survey for only 40 households, 10 from each category. Okay, so in the first round of survey, you collected random samples, okay, using the random sampling technique, but you did a short survey from these 111 values. From these 111 households, you did a very short survey. Okay, then you went, now you know for each household to which category they belong. So now you don't have to do the complete survey for the entire 111 households. If you need only 10 samples in each one of them, you will go to 10 from each category, because now you know to which category they belong, right? So you go to 10 households from each category and you ask them the complete survey. Okay, so there are 2 options to you. You do it completely randomly, so you will end up collecting data, complete data from more households. Like I said, if m is 10, you will collect complete data from 111 households. Or you can do a short survey. First of all, apply random sampling, find out how many samples you require. Then from those samples, only find out their category. their segment, and that's it, their type. And then you go back again for a full-fledged survey, and in that full-fledged survey, from each category you will take the required number, and that's it. Okay, so in the end you will collect 4 times m samples. In the second option, from each category you will just collect m number of samples, so in the end you will have full data from 4 times m samples. So in the second approach, the full data is coming, or n is equal to 4 times m. In the first approach, you are collecting full data from 11.1 m. Okay, so like I said, you can do it in stages, and you can save the number of samples. You can save your effort. Okay. Yeah, conceptualizing of sampling means how do we see the sample and how do we relate it to the population. Okay, so P means population. Okay, F means characteristics of the sample. I means the choice of the travelers. Okay, choice meaning how many trips they want to take, what mode of travel they are selecting, and so on. So this is I is their choice. Okay, and X is their attributes. X are their attributes, their personal attributes or the attributes of their trips. So for example, age, gender, income, car ownership, these are the attributes of the traveler. Or walking, waiting time, travel time, cost, these are the attributes of the trip. Okay, so X is a vector which includes all the attributes of the traveler and the trip. Okay, so how do you calculate the characteristics of a sample using the 3 methods of sampling which we have discussed? So we have discussed random sampling, stratified sampling, and choice-based sampling. Okay, so if you are going for random sampling, then the probability of a traveler selecting mode I given his attributes and theta. What is theta? Theta is the model parameter, the coefficient of the model. Theta is the coefficient of the model, the one which we showed as beta in the previous chapter. So beta and theta means the same thing. Okay, the coefficient of x1, x2, x3, and so on. Okay, so the characteristic of the sample traveler to select mode I depends upon X and depends upon the parameter of the model, and this would be equal to the possibility of the entire population to select mode I given its characteristics and the mode choice parameter. Okay, so you can see F is almost equal to P. For random sampling, they are equal because you are collecting the data randomly. So the percentage of people who will select mode I in the sample should be the same as a percentage of people who are selecting mode I in the population. This is the basis of random sampling, that the proportion should be same for the sample and the population. Okay, for a stratified sample, stratified meaning what? Let me explain again. Stratified means that you have divided the population according to some of the characteristics. Okay, so for example, you divided the population according to their age. So you are now collecting random samples from old people and young people, 2 different samples. Okay, so in stratified sampling, the choice of having of selecting mode I depends upon, again, it depends upon the probability of the person to belong to X category, okay, multiplied by the probability of selecting mode I, provided that he is in the X category. Now, what does it mean? For example, you have, let me go back. Okay, with car, okay, so we have 2 categories, right? With 4, or let's say 2 categories here, 4 or less members and more than 4 members. Okay, and you are collecting random samples from this category and this category. Okay, so the choice or the probability that a person will belong to this category depends upon the total probability that the person belongs to this category, which is 9%, multiplied by the probability that this person has a car. Okay. The possibility of a sample to be in this
25.
category. Sorry.
25 will
Yes,
be the possibility. Yeah.
yes, you're right. Yeah. So the possibility that the person will have a car, that is 25%. So the person belonging to this category has a possibility of 25%, and a person having 4 or less household members and having a car is 9%. Okay, so if you collect any sample, the possibility that in that sample you will find a person who has a car and 4 or less members will be 25 into 9%. 25%, which is the possibility for this entire segment, into 9%, which is the possibility to have a car in this whole category. Okay, so 25 into 9%. Okay, so if you collect any sample with stratified sampling, the possibility that a person will have a car and will belong to a household of 4 or less equals to 9% into 25%. Okay, what is 25%? 25% is the possibility of that person to have a car, and 9% is the possibility that this person belongs to a household of 4 or less members. Okay, so P of X meaning the possibility of being in a particular household, and Pi of X means having a car provided that he is in the X household. Okay, so like I said, you are multiplying them. Okay, then choice-based sampling. So like I said, in choice-based sampling, you are basically dividing the population according to their choice. So the probability, the frequency that a person you have collected through choice-based sampling will opt for choice I can be calculated in this manner. Okay, so this is the choice of I in the entire sample. Okay, choice for mode I in the entire sample. This is the possibility of a person selecting mode I in the entire population, provided that he is from X category. Okay, and this is the total possibility of this person belonging to X category. Okay, divided by summation of the same thing. Okay, the things which I mentioned here. Okay, so Fi means the possibility of the person to select I in the entire sample. Pix means the possibility of a person to select choice I provided that he is from X category, and P of X means the total possibility of a person to belong to X category of the population. Okay, and you can use the same thing here as well. Now the good thing here is that if you apply stratified sampling, then the possibility of a particular choice for any person is equal to the possibility of the choice for the entire population. Okay, so whatever the possibility of the choice in a sample is, that is equal to the possibility in the entire population. Okay, so but in the case of choice-based sampling, it is not the case. It is not true. Okay, let me show you with an example. So we have these categories. Okay, and these are the choices. Choices are bus and car. Categories are low income, high income, and these are their proportions. So low income bus users 45%, high income bus users 15%, total bus users 60%. Okay, total low income group 65%, total high income group 35%, and so on and so forth. Okay, now you can take the sample randomly. Okay, the first option is take the sample randomly. In that case, you should be getting the same proportion. Okay, so in that random sample, So for example, if you took 100 values randomly, out of those 100 values, how many people should belong to bus users low income group? 45. Okay. How many people will belong to low income car user group? 20. Okay. So whatever percentages are shown here, they should remain the same in the sample as well. This is the first case, which is random sampling. So you collected the data randomly, completely randomly, without any choice, and you got this. Okay. Second option is take an exogenous sample. Exogenous means now you are doing some selection. Okay, you are doing some selection now. Before you go there in the field collecting the data, you have done your selection. Your selection is that the data which you are collecting, you will collect 75% of the data from low income group and 25% from high income group. Why you are doing that? I don't know. maybe low income people are more willing to answer than high income group. Okay, or low income group are more easily available than high income group, maybe. Okay, so because of any reason, the data which you collected in the end was not 65% low income, 35% high income. You ended up collecting 75% low income group data and 35% high income group data. Okay, now in that data, what is the possibility that a person will choose a bus provided that he is in the low income group? What is the possibility that a person will choose a bus from the sample? Okay, now I'm talking about the sample. So what is the possibility that in the collected sample has 75% low income group, 25% high income group? So from the sample, what is the possibility that a person will choose bus provided that he is in the low income group? So from these 75% people, what is the possibility that the person will be choosing a bus from the sample? Okay, so for that they are using the concept of conditional probability, which we discussed in the last chapter. So that's why we are going in the sequence. Okay, so in the last chapter we said that if you want conditional probability, then this is the method you calculated. So I want conditional probability of bus provided that he is low income group. Then the equation was that first of all take the intersection of probabilities of these two divided by the total probability of being in the low income group. Okay, first of all take the intersection of probability for being bus user and low income divided by the total probability of being low income. Okay, so you can see it over here, probability of low income and bus. Okay, the intersection is 45%, so 0.45, divided by the total probability of being low income, which is 65%. Okay, so 0.45 upon 0.65 will give you the conditional probability that a person will choose bus and he will belong to a low income group. Now this is for the entire population, not for a sample. This is for the entire population. So if I go back, okay, this is this value. Now you can see here they are multiplying. Okay, it's not here. Sorry, forget about that. Okay, so now you can see that this is for the entire population. If I had, so for all the low income group people, they have 69.2% probability of choosing the bus. From the low income people, they have 69.2% probability of choosing the bus. Okay, so what is the probability of from the sample that they will choose a bus, that a low income group person will choose a bus? So you take the probability, which is normal general probability, and you multiply with the probability of low income group from the sample. So from in the sample I have 75% probability of being low income. Okay, so a person being low income has 69% probability of choosing a bus. So in the entire sample, I will multiply 69.69 with 0.75. This will give me the probability that a person will choose a bus from the low income group of the sample. Okay, so if the sample was exactly equal to the population, which is in the first option, if you take the sample randomly, then this will remain as it is, because in the end you will collect total 65 low income group and 35% high income group. But since this is not the case, you have taken the sample by selecting it, and you have selected 75% low income group people. So out of these 75%, what is the probability of choosing the bus? 69%. So now if you want the combined probability that a person will choose bus from low income group in the sample, then you multiply them. You multiply the probability, the general probability, with the percentage of that group you have collected in the sample. Okay, so you can see the table over here, but let us do some calculations ourselves so that you get a better hold of the idea. Okay, so I need a table here. I'll do the calculation in table, inshallah. So I need 1, 2, 3, 4. 1, 2, 3, 4. Okay. Okay, so bus, car, total, low income, high income, total. The first one they have already done it, okay, which was 0.692 into 0.75, okay, and this is whatever 0.519. Okay, now if I'm doing the same thing for high income group, okay, so again I will calculate the conditional probability that a person will choose a bus from the population and he is from the high income group. Okay, so first of all I need the intersection probability, which is 15%, so 0.15 divided by the total probability of being in the high income group for the population, which is 35%, so 0.35 multiply by the high income group I have collected in the sample, so which is 0.25. Give me this value. And then you will do the same thing this one as well. And this will remain as it is because of the total probability of high income group. The intersection will change, which is 0.20 now. Okay, and then if you do it for the low income group, then it will be the intersection of car and low income in the population, which is 0.2 divided by total low income, which is 0.65 multiplied by the population of low income you have covered in the sample, which is 675%. Okay, so give me these values. Yes. You can calculate
1.7.
1.7. How is it possible?
0.5 over 0.35 times 0.25, right?
0.25 is not in the denominator.
Ah, it's up, okay. 0.1.
0.1. Okay, same thing here as well. This should be 0.15. This is 0.1. This should be 0.15.
0.14.
14 something, right? Or
Yeah.
this one was
142, yeah.
1 4. Okay. And what about this one?
$0.173.
Okay. Now, if you do the summation for low income group, you should approximately get the same percentage which you have taken in the sample, 75%. Okay, and if you do the summation for high income group, you should again get approximately the same which you have taken in the sample, which is 25%. Okay, approximately. There's some rounding off here, I know. And if you do the summation for them, you will get 0.619. Okay, and for this one, if you do the summation, how much you are getting? 0.3 something.
0.313.
313. Okay, so this is 61.9% people from the sample are choosing bus. 31.3% people from the sample are choosing car. Okay, and as I said earlier, you already stratified the samples, so 75% belong to low income, 25% belong to high income. Okay, now if we apply choice based sampling in this case, so now you are taking the exogenous sample on the basis of choice of the travelers. Okay, so 75% car users and 25% bus users. Okay, 75% are car users and 25% are bus users. What will happen in that case? Basically, these conditional probabilities will change. The conditional probabilities will change. Okay. So let me take the table from here, copy it here. Okay, so for example, now 75% are bus users, 25% are car users, right? Yes. Okay, so I will multiply by 75% if I'm calculating bus users, and I multiply by 25% if I'm calculating car users, like we did in this case. Now, what will be the difference in the conditional probability? The conditional probability will be for people who are choosing bus, people who are belonging to low income group, provided that they have chosen bus. Okay, so people who belong to low income group, provided that they have chosen bus. So it will not affect this term. Okay, so this term will remain the same. The intersection will remain the same, but the denominator will change. Okay, so it is 0.45 people who are choosing bus provided they are in the low income group, divided by, okay, the total possibility of choosing a bus. The total possibility of choosing a bus from the entire sample, which is 0.60 now. So 0.6. Okay, and multiply by the percentage of bus users I have collected, which is 0.75. Okay, so in the entire population, this was the possibility that a bus user will belong to low income group, and in my data sample I have 75% bus user, so I multiply by 75%. Okay, same thing here, this will not change and this will be 0.60. Okay, and this will again be 0.75. Okay, so the denominator has changed because now I have reversed the situation. Earlier, when I was doing this, my condition was that he will choose bus provided that he is high income group or low income group. Now I have reversed the condition. The condition is he will be in low income group or high income group provided that he has chosen the bus. Okay, so the condition goes in the denominator. The probability of the condition goes in the denominator. So here the condition depended upon his choice. Okay, that he will choose bus provided that he is in a low income group. Okay, so I use a total possibility of being in the low income group or being in the high income group. Here I am saying that he will belong to low income group or high income group provided that he has chosen the bus. So in the denominator I will use the condition which is already provided, Here the condition provided that about his household, low income, high income. Here the condition provided to us is about the mode choice. Okay, so you will use a total of the probability of the mode choice. Okay, so give me these values now. As it is 6. The choice of being a car user, total choice of being a car user is 0.4. Okay, so in the denominator, you will use the total probability on the basis of which you have divided the data. Data is divided according to choice, total probability of each choice. Okay, and so on and so forth. Okay, now these totals, the total for each mode choice will be as per what you have selected for the data. So I have selected 75% of bus users and 25% of car users. Okay, so this will come to that. Okay, there's no problem with that. Okay, the only thing is now you will change these probabilities. Okay, the table is given here. Okay, you can calculate the values and check it from here. Sorry, you can check it from here. Okay, if you have any questions, please go ahead, ask me. Any questions? There's a small portion remaining with this example. It will continue in the next class, inshallah. Any questions, any problems, any confusion, any suggestions, queries?
No, thank you, Doctor.
Okay, okay. The nice thing about these classes is at 7 p.m. nobody has anything to say. It used to happen when we were studying as well. Okay, and it still happen when we have a meeting at late in the evening. Okay, so I can understand. If you have any suggestions, queries, you don't want to say it now because it will prolong the time. You can message me anytime. Okay, I don't mind. I don't mind totally. Okay, you need me to correct anything. You need me to do something.
Doctor.
Yeah, do tell me. Okay, it will be a favor for me.
Inshallah.
Okay? Thank you. Thank you. So have a nice
Bye-bye.
week, inshallah. See you guys tomorrow. Or not tomorrow.
Inshallah.
Next week, inshallah.
Next week.
Yeah, sure. 3 hours enough for 1 week. Thank you. Assalamu alaikum.